Hello everyone, my name is Li Songfan. I'm a PhD student in UESDC. Today, I'm happy to share with you our recent work on Internet of Things. IoT has become a part of life. Sensors give us a reliable way to sense physical conditions. Then, wireless communication makes end devices easy to upload their sensing results to Internet. In the current design of end devices, a microcontroller has to be employed as a master to operate various sensors and deal with wireless communication. However, the use of microcontrollers introduced two intractable problems. First is high power consumption. Recently, backscatter has significantly reduced the power of radios down to only microwatts. But many off-the-shelf microcontrollers still consume milliwatts power, so MCU becomes a major bottleneck for energy optimization. Second, the end devices need for reconfiguration across different sensors. If we change the sensors, we have to rewrite the embedded code, change the hardware connection, and even make a new PCB, which make reconfiguration so difficult. In this work, we take the first step to ask a bold question. Can we take the microcontroller away from the design of end devices? If we can do this, we can reduce the major power consumption from the current design and eliminate the need for embedded programming for much easier reconfiguration. Here, we envision the Internet of Microchip architecture. The control of sensors is offloading to a gateway, and the gateway has direct access to the sensor chip via wireless communication. This architecture brings some interesting features to end devices, including ultra-low power due to the elimination of microcontrollers, and is easy to reconfiguration because no need for embedded programming. In addition, many sensor chips have a standard interface to be accessed, for example, SPI and I2C bus. This architecture allows the standard sensors plug and play on the end devices because they have the same interface. However, it's quite challenging to achieve this vision. The key challenge lies in the fact that in traditional design, the MCU is employed to receive baseband signal from the radio and operate sensors through a standard bus. Without microcontrollers, how to leverage the radio to direct talk to the sensors? We address the challenge and build the first proof of concept for Internet of Microchips. On the downlink, the gateway directly controls the SPI sensor using radio-to-bus communication, which we call R2B. We highlight the concept of R2B as a novel communication paradigm that allows direct data exchange between radio and bus. On the uplink, the end devices conveys sensor results using SPI backscatter to save the power. In the following content, we will present two main technical aspects. First, we introduce the radio-to-bus communication to leverage the radio to communicate with SPI bus. The problem to achieve radio-to-bus is the totally different communication types between baseband and SPI bus. The SPI requires data and clock, two signals for data receiving. To convey SPI symbols on the downlink, we leverage PIE format to stitch data and clock information together. But the PIE and SPI have different symbol definitions and synchronization scheme. For example, PIE needs 1 while to transmit data, but the SPI needs 2. To overcome this problem, we design a PIE to SPI demodulator to directly convert the PIE symbol to SPI symbol. The PIE symbol is first input to a voltage integrator, and we can discriminate the PIE data according to the peak voltage by a threshold. On the other branch, the PIE signal is also converted to a clock signal through an inverter gate. The clock is used for further SPI bus communication. Then, the discriminated data will be adapted to transmission on the SPI bus to sensors. You can see that the PIE baseband signal is directly converted to SPI signals by a simple analog circuit. Now we have covered the first aspect. Let's go on to the second. How does the SPI sensor send data back to the gateway? To achieve the SPI backscatter, we have to solve two problems. First, the output of sensor data should be driven by a reference clock signal provided by the MCU. Without the MCUs, how to generate the SPI data output? Second, assume that the sensor has generated the data and conveys it using backscatter, but the receiver lacks the SPI clock information and cannot receive the correct data. Our basic idea is to leverage an external clock from the gateway. The gateway performs a downlink PIE transmission to deliver data and clock to the sensor. And the clock is also used to generate the output data. Then the output data will operate the backscatter switch to reflect the PIE-F signal. Given that the downlink signal contains the clock information, the backscattered signal can be successfully received at the receiver. We implement our prototypes as proof of concept. You can see it, no MCU, no processors, even the logic circuit is implemented by discrete gates. We also implement the logic circuit with FPGA, so that we can easily change the logic and quantify power consumption. Our current prototypes can achieve up to 200 kbps data rate, and the power consumption is 4.5 times lower than existing backscatter sensor platform on average. We implement the R2B gateway using USRP and explore it to communicate with the prototype in experiments. In experiments, the first question we ask is, what's the maximum range we can get? To answer this, we set up our system in the atrium on compass and measure the communication range. We first consider a static scenario, where we fix the distance d1 and move the receiver away from our prototype. As we expect, the RSSI decreases along with d1. When d1 is equal to 3 meters, the maximum d2 is around 30 meters. The next scenario is mobile. We move the prototype from the transmitter to the receiver at the speed of 1 meter per second. We got an interesting observation where the lowest RSSI is at the middle between the transmitter and the receiver. As a result, if we want to achieve higher RSSI, we can move the prototype close to either transmitter or receiver. This is because at this point, D1 is equal to D2. This setup can be treated as a monostatic gateway that combines the transmitter and the receiver together. You can imagine the RFID system. So, if you keep one link same and reduce the distance of the other link, the RSSI will increase. In addition, we also observe that this kind of effect is attenuating when the whole distance increases. Based on the Internet-of-Microchips architecture, we built two proof-of-concept applications. The first is a programming-free baseband. It includes an onboard accelerometer that is controlled directly by USRP through R2B communication. The ground truth we used is in the case with microcontroller. And I'm going to show you a demo video of the programming-free baseband. You can see that the USRP displays the XYZ information from the baseband. The cool thing here is that we don't need to write embedded code into the baseband. The second demo is a plug-and-play interface as an extension of our prototype. We built this interface to allow SPI chips plug and play. The following video will show you how it works. We want to add a humidity sensor to the prototype. First, we plug the sensor into the interface. Then we note the prepared script of the humidity sensor and the USRP. The USRP will automatically interface with the sensor and read the data back. We discuss some limitations of our current prototype. First, because we offload the sensor control to gateway, the wireless channel overheads increase. To investigate the overhead, we measure the channel use for 3 SPI chips. We note that the temperature sensor does not support continuous reading, which means that the gateway has to control the sensor before each reading. And then, the other chips support the continuous reading. We can only send the control at the first time and then read the data continuously. The right portion plots the channel use. You can see that the temperature has the lowest usage efficiency because a large proportion is used for control signaling. If the sensor supports the continuous reading, the channel overheads can be effectively reduced. The second limitation is no support for event trigger sensing. Some sensors provide a trigger signal to interrupt the MCU when they complete the sensor conversion. It's useful because the MCU can stay in sleep mode to save power until the trigger. But the gateway cannot detect the trigger signal because we offload the sensor control to the gateway, and the backscatter cannot talk first to inform the gateway. Our current prototype addresses this problem using an alternative solution. As we know which sensor we are using, the gateway can put a time delay before reading the sensor data. The time delay can be observed from the sensor specification. Here, we answer some frequently asked questions. First is about SPI clock timing. This is a standard SPI clock, and the clock frequency is fixed. In our current prototype, the clock is received from the PIE signal, and the clock frequency is changing over different data. Can sensor receive correct data with this clock? We answer this question is yes. To explain this, we know that the SPI is a type of synchronous communication. The clock signal drives the receiver circuit and determines where is the data, so the sensor can receive correct data. We also have conducted experiments to verify this view. The second question is how can we implement protocols to improve the communication? In our design, we remove the MCU, but we show that it's still possible to implement existing protocols. Compared to traditional embedded design, the logic in our architecture is peripheral. It listens to the R2B radio output and can enable or disable the SPI bus to sensors according to the specific protocol. One of the advantages of this architecture is that the logic will not change with different sensors, and the design of logic circuit can remain simple. because it only focuses on logic design without the signal processing to the baseband. Let's conclude this work. We introduce R2B communication for downlink transmission and SPI backscatter for uplink transmission. They together enable the vision of Internet of Microchips. With this architecture, billions of sensor chips can be directly connected to Internet. And the design of IoT end devices can be minimized. The keywords of those devices will be ultra-low power, programming-free, and plug-and-play. Thank you for watching. For more information, please see this link.